First, here at resting potential, we have, again, potassium concentrated inside, sodium concentrated outside. It's negative inside and positive outside. The potassium pretty much stays put because it has competing forces of nature. Its concentration gradient says leave, its electrical gradient says stay. It mostly stays. And the sodium-potassium pump ensures that that happens, which is the green one we're looking at here. The sodium has two forces of nature telling it to go inside the cell. They're saying as soon as those channels open, rush towards the negativity in there because you're positive, opposites attract. And they're also saying there's too much sodium outside, we need to spread it out and put some sodium inside. So that's what happens during the depolarization and rising phase here at step 2. The voltage-gated sodium channel opens, and this means the sodium channel only opens once it detects a little bit of a depolarization. So sodium channel opens, lets a bunch of sodium in, and that keeps depolarizing the cell so far that it goes up to positive 30, positive 40-ish, like we saw on our other graph. At that point, it's not going to keep getting more positive. And let's think about why. During this depolarization phase, we have let sodium rush in. When we did this, the voltage inside is now positive. There's not any more positive particles outside that want to come inside. Sodium's concentration gradient would tell it actually to leave. There's too much sodium inside now, spread out, because too many rushed in. Its concentration gradient would also say, wow, now it's positive in here. There's way too many sodiums. You need to go outside. Sort of like the bar example. If the bouncer let in too many dudes, they might decide they don't want to be in that bar anymore. They want to leave and go find another bar that maybe has a lot more ladies in it. That's what's happening with our sodium. And that is what causes at this peak, the sodium channels actually close. They're voltage gated, and when they reach this positive 30-ish territory, they close. Potassium channels are open at this point. Remember, potassium is also positive. The inside of our cell is now positive. Potassium now has two forces of nature telling it to leave. Its electrical gradient will say it is too positive in here, so leave where it's negative outside. And its concentration gradient is saying there's too many of you in here, potassium, so why don't you leave and go outside where there's not many potassiums. And that's our repolarization phase. We had, during phase 2, we had sodium rushing in, sodium gate snapped shut at the peak, and now we have potassium rushing out to restore our voltage difference. And actually what we have during this undershoot, which doesn't have a number on this graph, is that too much potassium leaves to the point where we're too negative now. So what happens in phase 4, when we're coming back to resting potential, is that our sodium-potassium pump makes sure to pump out all those extra sodiums that rushed in and pumps back in all of our potassiums that are supposed to be in here at rest. And then we get back to regular old resting potential, ready to do this all over again when we receive a message from another neuron. Something important to note about this undershoot or hyperpolarization is that it is a refractory period. The neuron might receive messages during this time from its neighbors. It might still be getting chemicals, but it cannot send an action potential during the absolute refractory period. And I was taught to think about this refractory period kind of like the one you might think of in sex ed or health class for the male ejaculation. There is a refractory period during which that cannot happen again, right? An absolute refractory period. It's just not going to happen, no matter the stimulation. And that's the same for this cell right now in the hyperpolarized state. As it's climbing back up to threshold or climbing back up towards resting potential, it's going to be more difficult for it to have an action potential. It would need a much stronger depolarization than usual, which is also similar in our sex ed example. It's technically possible to have an action potential at this point, but it is way more difficult. Another feature of this action potential is that it propagates all the way down a neuron. So we were only looking in those graphs at a little tiny slice of a neuron on the axon. But what we find is when we get one little part of the axon depolarized, so sodium rushes in, depolarizes it, makes it positive, etc., that is going to cause a little further down the axon those voltage-gated sodium channels to detect the voltage is getting higher over here and to open. And that's going to cause them to open and cause their own depolarization process. And all the while, The first part that got depolarized is repolarizing. It's in that falling phase, kind of going back to rest. And then while that's happening, we have the next little piece of the axon is doing this, starting the rising phase of its action potential, and it keeps going all the way down the neuron. Now, the myelin sheath affects this where we don't have to repeat this process for every little tiny section of the neuron. Imagine there was a myelin sheath around this axon where this green depolarized part had a node of RON VA and our other node of RON VA was right here at the end. We would actually see this first part get depolarized and be repolarizing, and our depolarization would jump all the way to the end, to the other node of RON VA. We wouldn't have to repeat this process during all the piece of axon in between. So that is how the myelin sheath created by the oligodendrocytes or Schwann cells in the peripheral nervous system speed up conduction along an axon.